Today we're going to learn about molecular effusion and diffusion. So, the dependence of a molecular speed on mass has two interesting consequences, and this is where the topic of effusion and diffusion comes into play. Effusion is defined as the escape of gas molecules through a tiny hole, so that's the key point there. So, let's talk about how things are escaping through this hole. One thing to note is that if the atoms are lighter, they're going to escape through the hole faster than atoms that are heavier. That also plays into the atom size. Smaller atoms tend to fit through that hole better than larger ones, so they're going to escape faster as well. And then also note that faster atoms are more likely to hit the hole, and that's because faster atoms are typically the small ones at that same temp. Now, diffusion is defined as the spread of one substance throughout a space or throughout a second substance. A good example of diffusion is if you put aerosol, once you spray it out of the can, it's going to diffuse through the air, which is that second substance, and spread out to fill a room or a space. With diffusion, one thing to note is that this is going to be faster for molecules that are lighter than those that are heavier. And also note that this is going to be slower than effusion due to these molecules act in a random motion and there are random collisions. And there are no direction that these are heading, they're just bouncing all over the place. So due to these molecular collisions or collisions between these atoms and molecules, the directions of the way that these gas molecules are moving is constantly changing. And we call this path that they are traveling a mean-free path. To define it a little bit better, this is the average distance traveled before that atom or that molecule collides with another. So this plays into pressure. Typically, if something has a high pressure, the length that they're able to travel before they collide is actually very short. They can't go very far and then all of a sudden they're hitting something. Whereas low pressure, these molecules can travel pretty far or a long distance before they're hitting another molecule. And that plays into, remember, collisions and pressure are directly related. Higher the pressure, the more collisions. So the effusion rate of a gas was developed by somebody called Graham, hence why it's called Graham's law of effusion. This law states that the effusion rate is inversely proportional to the square root of its molar mass. And we have to assume that both of the gases that we're working with in this equation are the same temperature and the same pressure, and they have identical size pinholes. Graham's law is as follows. R1 divided by R2 equals the square root, and then the M is the molar mass of gas 2 and the molar mass of gas 1. So let's break this down. R tends to stand for the rate of effusion, so how fast does that gas move? And then the other thing to note, when I'm talking about rate, I'm talking about the speed as well. You might also hear it be referred to as the ratio of the speed because it's giving a ratio of the speed 1 and then speed 2. Also note that 1 is typically your first gas and 2 just means you're working with the second gas. M stands for molar mass, and note that the molar mass here is grams per mole like it traditionally is. So let's work through an example. It says an unknown gas composed of a homonuclear diatomic molecule effuses at a rate that is 0.355 times the rate at which O2 gas effuses at the same temperature. Calculate the molar mass of the unknown and identify it. Well, let's break this down. First, homo, that means same. So it's an atom that's the same. but it's diatomic, so there's 2 of them. Well, we only have 7 diatomic molecules. We have H2, O2, N2, I2, Cl2, Br2, so 1, 2, 3, 4, 5, 6, and F2. I've always explained these as like Brinkelhoff. So now we have to set up our equation. Remember, our equation is R1, R2 equals the square root of M2 and M1. Note that they flip sides, where R is on top, 1 is on top here, the M1 is on bottom. So let's break down this sentence. We have to be able to tell who is gas 1 and who is gas 2. So it says my unknown is at a rate of 0.355. So I'm going to make my unknown gas 1, and then it says O2, we're going to make that my gas 2. So for my unknown, my R1, it says my rate already. It's 0.355. And then it says times the rate. So that's 0.355 times, and we're always going to put that over 1 if you hear that statement. Okay, and this is going to equal the square root of my molar mass of my gas 2, which means I have to figure out my molar mass of oxygen. So 15.999 times the 2 that I have, you're going to find the molar mass of oxygen is 31.998. And then it's asking you to calculate the molar mass of your unknown and identify it. So I'm going to put an X down here. Then we just have to solve. So when you're solving this, you're going to notice that your X here is underneath a square root. So we have to undo that square root. To undo a square root, we're going to square this problem. Don't forget, if you square on the right, I also must square on the left. So when you take 0.355 squared, you get 0.126025, and this is again all over 1, equals 31.998 over x, because all it did was get rid of this square root. Then you guys can go ahead and solve like a traditional problem and do your cross multiply and divide. So if you cross multiply, you get 0.126025, x equals 31.998. Of course, you're going to divide by the number attached to x, and you're going to see that your x equals 253.9020036. So what you should do next is then make sure you're rounding to the correct number of sig figs. Here, I'm going to round to here. This is easiest. 254. It asked us to calculate the molar mass, so that's grams per mole. Now, what is the unknown gas? We have to identify it. It's got to be one of these 2. I know that it's diatomic, so this molar mass is multiplied by 2. So what you could do is you could actually take 254 and divide it by 2, and you are going to see that 254 divided by 2 gets you about 127. Let's look at the periodic table and see which element is about 127. You're going to see that it's going to be really close to I2. If we go on to the next problem, it states a sample of hydrogen effuses through a porous container about 9 times faster than an unknown gas. And I want to calculate the molar mass of the unknown gas. Again, we're going to have to distinguish who is gas 1 and who is gas 2. So here, one thing that we need to know is it says hydrogen gas. Hydrogen we listed on the previous slide as one of our diatomics. So remember H2, O2, N2, Br2, F2, I2, and Cl2. So one thing to know about hydrogen is it's going to be H2 if it's in gas form. We're going to also denote this as gas 1, and then our unknown gas is gas 2. Then we have to plug into our equation. So remember, the rate of gas 1 has to go on top. So it says hydrogen is 9 times faster. So 9 over 1. This is going to equal the square root. Now remember, in our equation, M2 is on top. So here it says unknown gas, that's our second gas. Well, we don't know that, so we're going to put an X. And then our M1, so gas 1's molar mass, has to go on bottom. Remember, hydrogen is H2, so we're going to put that on bottom. So 1.0079 times 2 gives me H2's molar mass as 0.158. Then you guys can go ahead and solve just like we did on the last problem. We're going to square both sides to get rid of that square root. So 9 squared is 81. And this is going to be equal to x over 2.0158. Then what we're going to do is we're going to simply cross multiply and divide. So we're going to find out that x equals 163.2798 grams per mole. Here it just says 9 times faster. 9's not really a number. I'm really not going to mark off for sig figs here. So if you're okay writing this number, I'm okay taking that number. Here I have one for you guys to do for your homework, so I will link this PowerPoint so you're able to do that. But let's go do another type of problem. Here we're going to work a little bit differently. We are given the molar masses and we're going to try to find the ratio. It says calculate the ratio of effusion rates of N2 gas to the rate of O2 gas. So it's telling us that we want our rate to be N2 over O2. That's what we're trying to find. So we're going to make this one gas 1 and this one gas 2. So we're going to make our rate N2 over O2 equals the square root. Now, since I denoted this as gas 1, remember it goes diagonal. So I'm going to find the molar mass of N2 and put that on the bottom. And then O2 is gas 2. So remember, molar mass of gas 2 goes on top. So I'm going to find that for O2. Oops, that's 998. From here, I like these problems because you don't have to undo that square root. You can just throw this in your calculator. 31 divided by the 28, and then make sure you square root that number. And you're going to get x equals 1.06874447. Now this is a ratio, so ratios, fractions, don't have a unit for this. You have to compare it. So the ratio, remember, this is N2 compared to O2 gas. So we have to write a sentence. In order to get this 100% correct on your homework, you have to give me a sentence to describe it. So this states that N2 effuses 1.06874447 times faster than O2. Here I have you for homework to try out this one. Now we're going to go through one more type of problem so that you can see another way that this is worded. It says if a molecule of neon gas travels at an average speed of 400 meters per second at a given temperature, find the average speed of a molecule of butane gas, which is C4H10, at the same temperature. Note, we're not trying to find a ratio. We're not trying to find molar mass. We're actually calculating for a speed. That's why this problem is a little bit different. So let's figure out how to set it up. Remember, R1 over R2 equals the square root of M2 over M1. Let's type in and figure out which gas are we going to designate as gas 1 and which gas are we going to designate as gas 2. Since neon's listed first, I'm just going to go ahead and denote that as gas 1 and butane as gas 2. Here it says neon's speed. It tells me that. So that's going to go in for R1. So 400 meters per second. And it's asking me to find the speed of butane. So I don't know that one. I'm going to put that as x. And this equals the square root, and I've got to figure out their molar masses. Well, neon is a monoatomic atom. It's a noble gas. That's why it's monoatomic. It loves to stay by itself. It's happy. So if I find neon in the periodic table, neon, since it's gas 1, is going to go on the bottom, and its molar mass is 20.179. And then I'm going to find butane's gas. So I have to figure out the molar mass of butane. And if you look on the periodic table and add those all up, you get 58.123. This problem is solved pretty easily. Here we have 400 divided by x equals the square root of this number. Since x is not underneath that square root, you can just go ahead and plug this right-hand side of the equation into your calculator. 58 divided by 20, and then square root that number. And you'll get 400 over x equals 1.697165485. So remember, this is the same thing as saying this over 1. We can cross multiply and divide. So 1.697x equals 400. And when we divide by that 1.697, we're going to find out that x equals about 235.6870933. Since we are given an actual number in this problem, I'm going to go ahead and round to 4 sig figs, 235.7. Here's where other people kind of mess up. It's asking for speed here, so you actually have to have a unit here. So your unit is meters per second. Now, a couple things before we finish out. I want to discuss about this speed. Note that this speed here is slower than the speed of neon, and that should make sense. Butane is heavier, so it should be slower. So that's one way to check your answer. Just like before, I've given you one of these problems for you to practice at home. You should have 3 homework problems. And if you run into any questions whatsoever, please make sure that you reach out and ask. And I hope you guys have a great day.